talks cannot be delivered in person. So the next 2 talks are going to be given remotely. They had to change last minute, and this is the only set of talks that are going to be given remotely in this event. So I understand Lakshmi is the hello.
Yeah, Sai Lakshmi Bhavna. Yes.
Perfect. So can you please share your screen?
Yeah.
Okay, perfect.
Is
Thank
it
you.
fine? Yeah.
Yeah, it's playing fine, and hold on, let me make sure we can see you.
Yeah, it's playing fine, right?
Yeah, it's playing and we can see you. Okay.
Okay.
Excellent. So the next talk is on SIMC, ML Inference Secure against the malicious clients at semi-honest cost. Lakshmi is going to give the talk, and that's going to work with Nishan Chandran, Divya Gupta, and Akash Shah. Thank you so much.
Yeah, thank you. Good morning, everyone. I'm Sai Lakshmi Bhavna Obatu from Microsoft Research India. And in this talk, I'll discuss high-level ideas of our result called SIMC. And this work is published at Unix 22. So the problem of inference is as follows. Here are 2 entities, a client who holds his sensitive medical data and an insurance company that owns a well-trained machine learning model, which could classify clients as low risk or high risk based on the client's medical data. Both the parties want to learn this classification. A naive way to do this would be for the client to send his data to the server, who then learns the inference and shares the result with client. But the problem with this naive solution is that it does not preserve privacy of the parties, as the server learns the sensitive data of the client in clear. So secure inference tries to solve the problem of inference in a privacy preserving manner. 2 threat models considered in applied literature for the problem of secure inference are the semi-honest model, where both the parties, the server and client, are honestly participate in the protocol execution. And because of this weaker threat model, in this model, we have super efficient protocols due to results like Guzzle, Minion, CryptoNets, Delphi, SecureML, Siren, CryptFlow2. And the other stronger threat model is the malicious model, where one of the parties can choose to arbitrarily deviate from the protocol. Because of this richer security guarantee, the protocols in this setting turn out to be highly expensive. Bridging this gap, another interesting model that was introduced for secure inference is the client malicious model, where the server is semi-honest, but the client could behave maliciously. This is a reasonable model, as there are scenarios where the server is reputed and may not have any vested interest in cheating the client, whereas usually thousands of clients interact with the server, and it's unreasonable to believe that all the clients would be semi-honest. This model was introduced in the result called Muse, which was authored by Lay Mukul Mishra, Srinivasan Adapopa, which was published at Usenix 2021. In this result, they also give explicit model extraction attacks against existing semi-honest secure inference protocols, which are much efficient when compared to just black box access attacks when the client behaves maliciously. And this paper also builds secure inference protocols in client malicious model. But this protocol, though it provides this intermediate secure protocol that's secure in this intermediate threat model, this is much less performant than the state-of-the-art semi-honest protocols. So this made us wonder if we could build secure inference protocols in the client malicious model that are as efficient as semi-honest protocols. And with our work, SIMC, we could positively answer this question. And SIMC stands for Secure Inference Against Malicious Clients. Heading into technical details, the building blocks that we use are as follows. We use authenticated shares, which are in the client malicious setting, which are defined as follows. So 2 parties, the server and client, are said to hold shares of a field element X if the server and the client hold X0 and X1 such that X0 and X1 sum to X. And authentication of an element X is defined as alpha into X, where alpha is a uniform MAC key that is chosen by the server. And the parties are said to hold authenticated shares of X if they hold shares of both X and alpha X. The security guarantee here is that given authenticated shares on X, the client cannot forge authenticated shares of any X prime not equal to X by locally manipulating his shares. By cannot, I mean that this is only possible with negligible probability. The next building block is a garbling scheme. So at a very abstract level, a garbling scheme can be viewed as a functionality that allows two parties, a garbler and an evaluator, to evaluate any Boolean circuit C on their private inputs A and B respectively. For simplicity, assume that the circuit just outputs one bit. Then the garbler inputs his input A to the scheme and the evaluator inputs B to the scheme. And then as the output from the scheme, the garbler learns a pair of uniform labels denoted as K0 and K1, and the evaluator learns the label KC, where C denotes the output of the circuit evaluation on A and B. The output of the scheme, which are these uniform keys, can be later used by the parties to learn the circuit output. We call this procedure as degarbling, where the garbler sends two ciphertexts, encrypting bits 0 or 0 and 1 using labels K0 and K1 respectively. And the evaluator can decrypt the ciphertext corresponding to KC to recover C. Due to time constraints, I haven't told you how the evaluator can locate which of the two ciphertexts to decrypt. And this can be done securely using the point and permute optimization. But for this talk, we'll not get into those details. The security guarantee provided by the garbling scheme is that each party learns nothing other than its own input and the output of the circuit evaluation, which is denoted by C here. And garbling schemes can also be easily generalized for circuits with multi-bit outputs too. Now, I'll go on to summarize our protocol framework. So typically, a neural network is a sequence of alternating linear and non-linear layers, where linear layers consist of operations like matrix multiplication, convolutions, etc. And non-linear layers consist of operations like ReLU, maxpool, etc. So the protocol framework is as follows. First, the client's input X is authenticated, and these authenticated shares are fed as input to the linear layer, first linear layer. And at the end of the linear layer evaluation, our protocol outputs authenticated shares of M1 into X, where M1 denotes the matrix to be multiplied in this linear layer. These authenticated shares are further fed as input to the next nonlinear layer, which outputs authenticated shares of F1 of M1 of X, where F1 is the nonlinear function that needs to be evaluated in this nonlinear layer. And this pattern follows. We use additive homomorphic encryption to perform linear layer evaluation, and more or less the ideas are same on how to evaluate linear layers with the prior work. And major contribution of our work lies in the nonlinear layer evaluation, and that will be the focus of the remaining talk. So let Y denote the output of the linear layer evaluation, the previous linear layer evaluation. So therefore, the protocol invariant, by the protocol invariant, parties start the nonlinear layer evaluation with authenticated shares of Y. Now, in this nonlinear layer evaluation, we need to be careful about three issues. Firstly, we need to ensure that the malicious client inputs the correct share of Y into the nonlinear layer evaluation. Secondly, we need to correctly compute the shares of F of Y given the shares of Y. And then finally, we need to ensure that the client feeds in the right share of F of Y into the next linear layer evaluation. These input consistency checks that we need to do in steps 1 and 3 are crucial and are responsible for major cost in use. Let's see how we tackle this, how to tackle these input consistency checks. So let's see, since the linear layer outputs authenticated shares of y, a naive solution could be to input the authenticated shares into the garbled circuit and reconstruct both y and alpha y inside the garbled circuit and check that indeed the authentication is correct. But this would involve representing the field multiplication as a Boolean circuit whose secure evaluation turns out to be expensive using garbling schemes. We provide a super lightweight solution for this issue in SIMC. On a high level, what we do is to re-authenticate Y with the help of a garbling scheme, with the help of a simple garbling scheme. That is, we compute another fresh sharing of alpha into Y using a garbling scheme that just reconstructs Y, which is just a simple addition circuit. Before going into how we exactly do this re-authentication, let's see how does this re-authentication help. Now, suppose that we somehow have this re-authentication, we need note that we end up with two different sharings of authentication of Y. One from the output of the linear layer evaluation, and another is the re-authenticated that we just computed. Now, with these two instances of the sharing of the same value, we can publicly reconstruct the difference of these sharings, and the server can check if the difference reconstructs, if the difference equals 0 or not. If it equals 0, it means that the same sharing of Y was used by the client in the nonlinear layer evaluation. If the difference is not equal to 0, then we detect that the client is cheating and we abort. So this is possible by the randomness of the MAC key that was chosen by the server. So here, this is how the re-authentication helps. And thankfully, we need not do this consistency check once for every nonlinear layer. And in our paper, we show how to club all these consistency checks for all the nonlinear layers together into one single consistency check that can be done at the end of the protocol before revealing the output. Okay, now let's see how do we actually do this re-authentication using a simple garbling scheme. We first garble a circuit that takes in shares of Y from both the garbler and the evaluator. So here the server is the garbler and the client is the evaluator. So the scheme just takes in both the shares and it reconstructs the shares of Y using a Boolean circuit, and then it output shares of Y. Note that here we'll just talk about the output of the garbling scheme and not the output itself. So instead of the evaluator receiving Y, the output Y itself, it would receive the output is as follows. As a result of this garbling scheme, for every ith bit of the output Y, the server who acts as the garbler learns a pair of labels ki0 and ki1. And the client who acts as the evaluator learns the label kyi, where yi is the ith bit in Y. Now, for each bit of yi, we slightly tweak the degarbling procedure to obtain shares of alpha into yi. The server chooses its share of alpha yi uniformly and encrypts 0 minus alpha yi 0 using the 0th label, and alpha minus alpha yi 0 using the 1 label. And he sends across these two ciphertexts to the client. And then the client, using his key kyi, he recovers alpha yi1. That by the definition of the ciphertext, it's easy to see that the reconstruction of the shares that the client and server hold are indeed reconstructs to alpha yi. Now that we have shares of alpha into yi for each bit of yi, for each bit of y, shares of alpha into y can be obtained by taking local linear combination of the shares with appropriate powers of 2. Summarizing, our solution ensures consistency between the output of the linear layer and the input of the next nonlinear layer by re-authenticating y with the help of a garbling scheme. And then we have seen how this re-authentication helps, and we have also seen how the re-authentication actually happens. Then we can use the same techniques to ensure consistency between the output of a non-linear layer and the input of the next linear layer. That is, we can actually use the above garbling scheme itself to also compute and output shares of f of y, and then we could compute shares of alpha into y in the same manner as reauthentication. And then we have also noted that we only need one single amortized consistency check at the end of the protocol. So just to give an example of analytical comparison of costs, we take the ReLU circuit as the nonlinear function, and then SIMC requires a communication of just 18 L lambda bits, whereas Muse requires communication of 293 L lambda bits, where L stands for the log of the field size that the computation goes in, and lambda stands for the computational security parameter. In our result, we also show how to push majority of cost to an input independent pre-processing phase. Okay. Now, finally concluding with the experiments, we do experiments on SIMC and Muse on benchmarks MNIST and CIFAR-10, and SIMC is 23 to 29 times more communication efficient than Muse, and it outperforms Muse by 4 to 8x in a high bandwidth setting, and it outperforms Muse by 6 to 11x in a low bandwidth setting. And surprisingly, SIMC also communicates 21% to 41% less than the state-of-the-art semi-honest protocol Delphi. Implementation of SIMC is available at this link. So, yeah. Thank you. Any questions?
Thank you so much. Let's thank the speaker. I'm not sure you can hear the ovation, but there are these people applauding.
Yeah. I could hear the clapping. Yeah. Thanks.
Perfect. Thank you. No, so you finished on time. We do have time for a question if the audience or people in Zoom have a question. So we have a question. Maybe you can say, yeah, as I mentioned. I don't think she's hearing you, so maybe you can come here or say it again and I will repeat.
So you said by this technique, you get around the field multiplication problem, but you would still need the field addition to be done in order to reconstruct the share, right?
Yeah. Field addition is quite cheap, right? If L is the size of the, if L is the bit length of the element, field multiplication would need L square and gates, but whereas field addition will only need L and gates, right? So it's much cheaper than field multiplication, and yeah.
Okay. Yeah.
That's quite bearable cost. Yeah.
Thanks.
Yeah.
Okay. Thank you. So let's thank the speaker again.
Yeah. Thanks, everyone. Bye.
Thank you, Lakshmi.